Hello, can you hear me well? Very good. Hi. Well, thanks for receiving me. I'm glad to be here. My name is Julien Van Egg, and I work at Bloomberg. So what is Bloomberg? It's a fintech company. People know us from the TV channels and things like that, but in fact, what we sell is a Bloomberg terminal, which every trader in the world actually has on their desk. And my job is to secure the software that we run. My talk today is about adversarial logic, and let's get into it. So in order to really explain what the landscape is about, I want to clarify some terminology. Verification, as we all aware, is proving the absence of bug. And verification does not admit any false negatives. Testing, on the other hand, is proving the presence of bugs, which does not admit any false positive. Exploitation is not verification or testing, it is to prove that you can compromise a program or a system based on an existing bug. So it assumes the existence of a bug and try to prove that this bug is actually a security flaw rather than just a benign bug. And that's what we're going to talk about today. So just a little trip down memory lane. Hoare logic, everybody's familiar with Hoare logic. Hoare triple, P, C, Q. So if you have a fragment of code C, and which starts in a state satisfying precondition P, and provided C terminates, then C will actually terminate in a state satisfying postcondition Q. For example, if the precondition is the fact that the variable x equals n, and your piece of code is if P, x plus plus, else x minus minus, then your postcondition will be, well, either P holds and x equal n plus 1, or P does not hold, not P, and x equal n minus 1. This is pretty ancient. Well, pretty ancient, I shouldn't say that, but it's 50 years old now. Way more recently, like a big jump in the future, Incorrectness logic, created by Peter O'Hearn and released at Popple 2020, is not about verifying the absence of bug, but it's about proving the presence of bug. And the triple, or the quadruple, you could say, in incorrectness logic is the following. You have still the structure P, C, Q, where C is a fragment of code, P is a precondition, but now you have two postconditions. One postcondition is what Peter O'Hearn calls the OK postcondition, Q, and you have another postcondition called the error postcondition that we note here, R. For example, if you have a piece of code that says that tries to put a value V in an array that starts at address P, and that P points on a valid location in memory L, then the postcondition of that statement will be that, well, P still points to the valid location in memory L, and L points to value V. So I'm abusing incorrectness logic here a little bit because I'm using the extension of incorrectness logic called ISL, Incorrectness Separation Logic, that was created by Raad and Peter O'Hearn and a bunch of other collaborators in the last couple of years. And therefore, my little example at the bottom use incorrectness separation logic. Another example is if P points to an invalid memory location, represented here as bottom. And say you try to put the value V at address P, well, what happens then is that you have an error, and that error is tracked through this error relation rather than the OK relation, meaning that you can actually interpret the program in two different ways. The first way being the regular, Hoare logic way, you could say, although it's an under-approximate interpretation, and then you have this error interpretation where you can track the error condition of the program. Well, let's try to have fun a little bit with incorrectness logic and find out what are the limits of incorrectness logic and what are a few examples that contain bugs that may not be that trivial to find. So I'm going to pass a few minutes explaining this. Assume you have two programs. You have a client and a server program in a client-server application. And let's look at the left column for a second. You have a secret, assuming for simplicity it's an 8-bit random value. And that server does the following. It's a while loop. It's an infinite loop. You can see at line 7. and it reads a specific value of a credential on the socket line 8. It checks whether that received value is equal to the secret. If it is, then great, at line 15 it will actually serve the client, and then it will return the error code at line 16. If the received value is not equal to the secret, if it's smaller than the secret, or if it's bigger than the secret on line 11, it will have an error code of 1, and if it's smaller than the secret, line 13, it will have an error code of 2. And that error code is sent back to the client line 16. So as you can see here, there is an information disclosure vulnerability in this server, because one can guess the value of the secret based on a logarithmic amount of attempts. The reason for this is because you can guess 1 bit of the secret at every interaction with the program. So that's exactly what our client is trying to do here. It tries, first of all, it takes an initial value, say the maximum value of the unsigned integer, line 4, and a step, say the half of the range. And then similarly, it uses an infinite loop to try every credential one at a time, and based on the return value, whether if it was a return value of 1, then it will know that it overshoot. Therefore, the next guess at line 10 will be guess minus a step. Or if the return value was 2, then it undershot, and then it will try to have a bigger guess at line 12. We said the next guess is actually guess plus 10. And by at line 14, the goal here is to actually guess the secret, meaning that the return value, you try to reach a return value that is 0, or a return code, I should say, that is 0. Why is this example particularly interesting? Well, first of all, when you realize this, let's come back for a second here, there is some kind of oscillation that's happening here. It's not just one interaction with the program that you need to formalize, it's actually a sequence of interaction with the program. So you keep going until you guess. So there is kind of this feedback loop between an attacker, the client, and the server that is vulnerable. So how can we prove the presence of a secret leak in this OBP, the Oscillating Bit Protocol, cute name? Well, what we'd like to use is to use incorrectness logic. We try to prove that there is a bug. We're not trying to prove the absence of bug here, but we're trying to prove that there is a bug somewhere. And a little insight is that we want to compose in parallel the vulnerable program that we're trying to prove buggy and the adversary. So the adversary itself is a program that is parallelly composed with the buggy program we're trying to prove buggy. And we enforce a strict separation between the program and the adversary. Strict separation because an adversary cannot view or cannot read the memory of the program directly. So the variable of the adversary and the variable of the program are strictly disjoint in adversarial logic. And what we try to do here is to basically augment the knowledge of the adversary as we go. So there may be a certain amount of feedback loop going on between the two, and it requires multiple execution to understand where the leak actually is. And a big difference between what I'm going to call traditional verification or traditional way of approaching the problem is that the assertions are given by the adversary. So the adversary is trying to prove its assertion rather than the program trying to prove its contract. It's a little bit of difference. Another way to look at adversarial logic is a marriage of incorrectness logic and something called the Dolev-Yao model. And most of you are familiar with the Dolev-Yao model, the Alice and Bob model, that is used in the verification of cryptographic protocols, where you're trying to prove certain properties of a protocol based on certain properties, for example, whether the attacker can read a message or after a certain amount of interaction between Alice and Bob. So if you take those two elements, incorrectness logic and the Dolev-Yao adversary, you mix them together, you obtain adversarial logic. You can think of adversarial logic as an implementation level theory of the Dolev-Yao model that works on code rather than models. All right, let's zoom in a little bit. Adversarial triples have the following syntax. First of all, it has sequential rules where you still have the OK interpretation or correlation that goes from P to Q by executing a piece of code C of P, say, for program. And you have the adversarial interpretation. So it's a generalization of the error interpretation, or the error relation of incorrectness logic. And in shortcut notation is this little epsilon. So when we have a series of rules that are valid for the program interpretation, the OK interpretation, as well as the adversarial interpretation. And when that is the case, instead of having two rules, we just have one rule, and we use this little symbol epsilon. That was also used by incorrectness logic. And we also have parallel rules. We mentioned the program and the adversary being composed. We need to introduce this parallel rule in incorrectness logic. And when we introduce this rule, we have a slightly non-standard way of doing so, meaning that we have two preconditions and two postconditions. So in some other logic, you may have a single precondition, say P star A, and a single postcondition Q star B. But in adversarial logic, in fact, we keep two preconditions and two postconditions. Adversarial logic is structured in three different fragments. The first fragment I call the core rules. The core rules are the same rules as incorrectness logic with symmetry restored. And I'm going to mention what I mean by that at the next slide. The next fragment is what I call the communication rules. The communication rules allow to talk between the two pieces of code. So there's a parallel composition, but also read, write, and com primitives. Read allows you to read a message, write allows you to write a message, and com allows you to share message between two processes. And then yet another fragment is called a knowledge rule. The knowledge rule has new rules that are new to adversarial logic. They're not present in anything else. One is called the parallel backward variant rule. The parallel backward variant rule is a generalization of the backward variant rule of incorrectness logic that allows you to basically select an iteration in the future when you deal with loops. And I'm going to show the rules very shortly. The adversarial consequence is a rule that is really important because it allows you to infer things like information disclosure where you cannot observe the information directly. So sometimes you may observe a value V, say, and by observing the value V, you know that there is a certain constraint in the program that holds. For example, when we observed that the return was 1, we knew that, well, our guess was not big enough. And we observed value 2, then we saw that our guess was too big. So this adversarial consequence rule allows you to basically convert the observation of a specific return code to an actual constraint that is known to the program only. And then success and failure rules that are slightly different, which I'm going to show right now. I hope you can see. All right, so the first big difference you can see between adversarial logic and incorrectness logic is that you have epsilons not only in the post condition, but also in the precondition on the left side. And that is relevant because this allows us to apply all these rules, not only for the program or for the adversary, but for any. So all of these rules that you can see here can be used whether you're interpreting the adversarial program or the program itself. The program under test, let's call it. So just to mention, can I actually use this? Yeah, very good. So the unit rule here, well, well-known rule, obviously. If you start in a precondition P and you do nothing, then you're still in P, in a state that satisfies P. The consequence rule is also a well-known rule that is also present in Hoare logic. However, there is a little inversion here. So basically, if you know that P, C, Q holds, and you know that P implies P prime, and also Q prime implies Q, then you can derive that P prime, C, Q prime. This is present in incorrectness logic as well. So all these rules are in fact present in incorrectness logic, and we just generalize those rules by having all those epsilon on the left here. That allows you to have a symmetry restored, one could say. Let's talk about a little bit more interesting rules that are new. Communication rules. One is read rule, the write rule, and the communication rule. So let's talk about the first one, and the write rule and the read rules are quite similar. But let's talk about the read rule for a second. Well, if you are in a state that satisfies precondition P and you execute read S, read on a channel, say, or socket S, and you store the value that you read in a variable X, well, what happens is that you have fresh variable that you create here. And, in postcondition, you basically have P where S prime replaces S, where X prime replaces X. And the new S is equal to the old S where you remove V and X equals V. So basically say you have so in adversarial logic, those channels or sockets are represented as lists. So basically what you're saying is that you're taking a value from the list and put it in X, and then S is the same as before, except it has one value less. Okay? And here the right rule, and assuming that you have a precondition P with a value of X equal V, and you're trying to write the value of X on the socket of the channel S, well, what you're saying is that there are fresh values such as the postcondition holds where where S prime replaces X, and S is basically the same as before, except that you add a value at the end of S, which is V, right? Which corresponds to what we're seeing here, where you have a certain value of S, you have a bunch of values in the channel already, and then you're adding one to the channel at the end. And if X is equal to V, then you put V at the end of the channel. And then the par rule, which is the one we mentioned before, where if you have two terms, typically one is a program term, the other is the adversarial term, and you want to compose them in parallel, well, you simply actually take the two preconditions and you put them here, and the two postconditions, you put them here. So that's interesting because this allows us to express a separation without a star operator of separation logic. And finally, the communication rule, well, provided you have a couple of terms that are composed in parallel, well, what you're saying here is that you're going to take a V of one of, say, the left side, and then you're going to put it on the other side. So it's basically, if you understand those two rules and this communication rule, it's just basically, provided you have a bunch of, you have value, say value S, and then you are just taking a value V in S, you're taking it out, and then you're putting it on the other side. Okay. Knowledge rules. This is the last fragment of the adversarial logic. All right, we do have, let's talk about these are simple. If you're trying to assert, the adversary tries to assert whether B holds or it doesn't hold. Well, if you know that Q holds and Q implies B, then you know that a Q holds, and then you're happy, you basically reach the goal, the adversarial goal. If you fail, however, you don't stop. If Q holds and Q implies that not B holds, and if trying to prove that B holds, then you don't stop. What you do is that you accumulate the knowledge of not B in the adversarial interpretation. So basically, you're not imagining our little example where we were trying to say that the return value was 0. Well, if it's not 0, you don't stop. You just stack up the fact that it's not 0, which implies a certain constraint of the secret. Then you continue until you actually can discover the secret. So that's the meaning of those two rules, that when you reach a success of the adversary is happy, but when you have a failure, you do not stop. You just stack that knowledge into the adversarial context. All right, and let's talk about this adversarial consequence rule, which is also quite interesting. Well, assuming that you have a couple of programs, one is the actual program on the test, and the other is the adversarial piece of code. And you know that if Q holds, then the program is going to write value V1 on the socket S. And on the other side, you have a piece of adversarial code, and it's trying to read a value on S. Well, what this rule says is that if V equal V1, if V1 equal V2, I'm sorry, well, you can basically derive the knowledge of Q without ever observing it. So basically, Q that is only present in the program interpretation here goes to the adversarial interpretation just right there. And you cannot express this rule without any combination of any other rule. So that's why it's a rule in the logic, because you cannot do this otherwise. Remember, because the variable of the program and the variable of the adversary are strictly disjoint. And therefore, if any variable actually appears in Q for the program, you have to do a substitution of variable here. However, the knowledge of the predicate Q can be transferred. And finally, you have the parallel backward variant rule. This is a generalization of the parallel backward variant rule, or of the backward variant rule of incorrectness logic, except that it's in a parallel setting. So, assuming there is an iteration that goes from n to n plus I, say, or normally plus 1, but let's say plus I for generalization. So basically, you can repeat that piece of code a number of times so that you can go you can exhibit a trace that goes from the initial state of the loop or initial state of the composition to a certain state n. And here, because you are parallelly composing the program and the adversary, in fact, what you're saying is that if you repeat the piece of program fragment n times and the piece of adversarial code fragment m times, then you can actually reach the state P of n and A of n by using the parallel backward variant rule. So that's interesting because this shortened the proof of the existence of bugs significantly. You don't technically have to have this rule. It's just a way to actually shorten the proof significantly, but you can express the same proof of bugs without that rule as well. All right, in a nutshell, adversarial logic is, to my knowledge, the first logic to analyze the exploitability of software bugs. So it's not trying to find bugs, it's trying to tell you whether bugs are exploitable, whether bugs are security issues. In the paper, if you're curious, you can see the denotational semantic as well as the soundness theorem, which is a new kind of soundness theorem, one may say, which is an attack soundness theorem, where you can prove the existence of attacks. And there is no false attacks, because we are in an under-approximate setting. So every attack is a true attack. However, adversarial logic does not guarantee that it can find all attacks. It's not. There's no result. There's no proof that it shows it can find all attacks. It only the soundness proof only allows you to prove that every attack they exhibit is a true attack. And this is the inviter.
Any questions? Yeah, I see. Ilya?
Should I just yell? Is it okay?
There's a microphone.
Oh, yeah, there was
for the audience.
Thank you so much. It's a very nice talk and a really nice application of the idea. So you haven't shown the proof, it's probably in the paper, of the oscillating bit construction. And you probably follow it.
This is just a basic example. If you look at the complete proof, this is just if you look at this example, that leads to proofs like that. If you want to see the entire OBP proof, you look at the paper, it's way bigger. If you don't use the parallel backward variant, if you use the parallel backward variant, it shortens the proof significantly.
Right, so I actually have a couple of related questions. The first one is, what's the story if you try to automate the inference of these proofs?
In terms of tooling, you mean?
Yes.
Right. Well, there's a whole field of tooling called automated exploit generation. And so far, the tools have been really addressing pockets of exploits, for example, stack-based buffer overflows. And this logic is meant to power the future tools for AEG. So it's a theory paper. It's not, we don't have a tool that actually implements adversarial logic right now. However, we believe that this new theoretical framework will actually empower new tools that will be able to express things much more powerful than, say, stack-based buffer overflows and things like that.
Okay. So the second related question. So from my very limited knowledge of something like return-oriented programming, it's not usually the case when you have your adversary called explicit that you can try to verify for the presence of exploit. So my question is, would you see that adversarial logic be helpful in generating the code for adversary?
It's a good question. So let's take this example here. In fact, one way to think of adversarial logic is it's a kind of symbolic execution where the symbolic values are only introduced by the adversary. So basically, you have values. You don't just to answer your question, or to go straight to the answer. We can have templates of adversarial code that you can use to actually like a library of exploit or like template exploit that you can actually instantiate based on specific patterns of interaction. And we do not provide a way to automatically generate the adversarial program right now. However, those templates allow us to express rather wide variety of exploits, which is more, here we talk about information disclosure, for example. It's not just about buffer overflows or your typical kind of exploit. It's actually cases where you have oscillation in finite state machine, as we saw in the OVP example.
Yeah, hello. So the rules that you were showing for this adversarial logic, they, like in incorrectness logic, look pretty much like strongest post conditions, kind of, also for the channel. If you were to define something like weakest preconditions, could you then exclude the presence of attacks? So have a correctness logic for this kind of adversarial scenario?
Both incorrectness logic and adversarial logic are under-approximate logics. Therefore, you cannot prove the absence of attack.
Yeah, not in your logic, but could you imagine defining a logic for excluding the presence of such attacks?
I guess so. I guess you could try to have a similar adversarial logic in an over-approximate setting. It's philosophically speaking, when you think of proving the presence of bugs, it's really inherently under-approximate because you're trying to prove a bug, you're not trying to prove the absence of bugs. So you could do it technically, mathematically speaking, you could do it. Whether that would fit the philosophical framework, I don't know.
Maybe we have time for one last question when the next speaker sets up.
I thank you for your attention.